Hi, and welcome to the section 1.10 pre-class video assignment. So we're going to cover the first 3 pages of the handout in the video, and we will cover the rest of it together in class. So today we are looking at something called Euler's method and some variations on that called improved Euler's method and the Runge-Kutta method, and we will discuss some of these other methods. But we're already just looking at some of the basics here. I'm going to have you try some of the basics before we cover the rest of it in class. So the point here is that there are lots of DEs that cannot be solved analytically by the methods we've discussed. Or methods we haven't discussed. So some of them aren't convenient to be solved analytically. But generally then there are what we call numerical methods that we might be able to use. So this is an example of it. So Euler's method, which is what we're going to talk about now, is basically a numerical method for solving a first order DE of the form dy dx equals f of xy. So again, remember when we read this, it is convenient to think that this is really telling us that the slope dy dx is given by some function of f with a coordinate point xy inserted inside it. And again, here we are going to talk about initial value problems. So they will have some sort of initial condition point. So before we get to Euler's method specifically, this is closely related to tangent line approximation, which we will have seen in Calc 1 at some point, that we can use close to a tangent point. You can use a tangent line as an approximation for a function instead. Again, so that is if you're dealing with a function that is difficult and hard to work with and complicated, you can, at least in the neighborhood of a tangent point, perhaps use its tangent line instead, and of course a tangent line is just a linear function, which is nice and simple and easy. So that's kind of the idea. So let's take a little look at this idea. This is also, you might be familiar with it, as called linearization, but linearization was just a term for the idea of using a tangent line to approximate a function close to the tangent point. So we have a little picture, something like this. Imagine we have a function, this blue line here, f of x, and we want to estimate it somewhere close to a tangent point here at x0, y0. So imagine the tangent line, which is hard to draw straight on this tablet, but imagine a tangent line that just touches at x0, y0. And then on this picture, you should be able to imagine what we are looking for here is that this point right here, the linearization at x1, is an approximation for the true function value y1 at that same point. Again, you can see the error. The error is the difference between these 2 points. And again, it looks like there's a big error here. This is somewhat counterintuitive in the sense that in order for me to draw it so that we can see it, I have to make it look like there's a big error. But again, typically, this is something we're doing close to a tangent point so that there is a small error, or imagine that we have zoomed in greatly on our point here. So that is the idea. How do we find this place, L of x1, to use it as an approximation for y1, the point on the curve itself? So the idea is to just find the equation of the tangent line, which we're going to name L of x, and then we can plug the input value into L of x instead of the awkward function f of x. So here is basically a little think through of how to come up with the formula for a tangent line. So at the point x0, f prime of x0 is your tangent slope, and the point on our tangent line will be the tangent point x0, y0. So by using the point slope form of a line, we can come up with this. That is, we're going to call the tangent line, instead of calling it y, we're calling it L of x. So we have L of x minus y0 is the slope times x minus x0. Solve this for L of x, and this is basically a formula for your linearization. And again, think of this as being, again, the slope is given by f prime of x0, and the tangent point is given by x0, y0. So this is readily available information, yes? So we can use a tangent line like this and make an approximation fairly conveniently. Another way of writing this, and sometimes convenient here, would be that basically this x minus x0 is really just representing some change in x, yes? So we often call this either a delta x. We've also called this an h. So basically that's what we're calling it here. If I call x1, if we're plugging in, so if we take our linearization function and plug in our point x1, that is an approximation for y1. And we have this guy here is the difference between the x values here, which we can just call h. It's also known as the step size. So here the idea is that I should probably say y1 is approximated by f prime of x0 times h plus y0. And again, h is x1 minus x0. So this is just using the tangent line. All right, so this is fairly doable. This is something you would have seen in Calc 1. Go ahead and give that a go here. All right, so to get Euler's method from this, there's a couple of things we just have to recognize. So the one part is in Euler's method, we are making lots of these steps, not just one step. Make lots of these steps, and of course for accuracy they should be lots of tiny little steps to follow, sort of trace along the curve to make good estimates. So basically here is our picture. The idea here would be that this is our initial value point here. This would be x0, y0. This is sort of your initial condition. Your initial condition point is here. And suppose that what we're trying to do is estimate this function value at x3. So the idea is, instead of trying to take one big step and getting a lousy approximation for x3, how about we take lots of little steps? So we start by computing a tangent line here and figuring out our tangent line here, and we move over a certain distance. And then the advantage of Euler's method is, how about we stop over here, recompute our slope, calculate a new tangent line, and follow that until we get over to y2, and then we can recompute our slope, come up with a new tangent line, and compute our new y3, and that should be more accurate than doing one big step. So that is just sort of repeating the method from this previous page, repeating this method multiple times along the route. So this should give us a better estimate than doing this once. A couple of notes here that for practical purposes, the step size, how far we step over each time, should be a constant. So this should always be the same value, h. We can then compute, or re-recognize this formula in recognizing these recursive steps. Again, this is a repeated process. We compute the next step based on the results of the step before it. So using this same formula, we can simply kind of re-index this, and that is, how do we find the subsequent y step? It is, we use the slope at the previous x step and the previous location, multiply by the step size, add the previous y output size. So this was the idea. So the point here is, this was based on, this is written in terms of following a known curve f of x. A subtle but important distinction here is, in a first order DE, what happens? What does this look like? We would get a y n plus 1 equals. So what gives us slope in a first order DE? The answer was, it's this function f of xy. That is what gave us the slope. So basically, we can say we do this recursive step. The slope is given by f of the x and yn, again, x and yn, times step size plus we need the y value at the previous step. So this would be written in terms of our working in a, basically think of it as working in a slope field for a first order differential equation. This is what it would look like because this is what gives you slope, right? F of x, y, and yn. And again, notice this is not a prime. It's not a prime there because f of x, y is the slope. Yes. So this is the recursive formula for doing this process for Euler's method. This is our recursive formula. So after the first step, you are no longer using a literal tangent to the curve. We are basically now in a slope field, and we basically have stepped over to a new estimate point in our slope field, and we now use the slope at that point of our slope field to be the slope for the next segment. Now, I think you can probably understand that. How is Euler's method accurate? Well, if you make big step sizes, it becomes less accurate. Making big step sizes is less accurate. And clearly, if you have to make lots of steps, that is also less accurate. A little secret here, Euler's method is not actually very great for accuracy. We would look at more complicated but more accurate methods when we talk about this together. But the basis for the process is this concept is important for Euler's method. So there are more accurate methods. Something you will see talked about is error. So we will talk about the absolute error in Euler's method. So absolute error is just the difference between the true value that you're trying to approximate and its approximation. In absolute value means, of course, the error was just a positive error. We don't care which way around these go. So you would just do the difference between the actual value versus the approximation in absolute value. Now, we will look at this to sort of demonstrate Euler's method. In the real world, realistically, this is not something that is computed. The reason you're doing Euler's method is because you can't find the actual value because it's too difficult or too awkward or not possible. So this is more of a teaching information or more for a illustration of the accuracy that we might ask about this. So you will see a couple of examples like this. So try a linear approximation method using a first order DE. That will be your next little example. Okay, once you have tried that one, the next question in my open math is a bit of a thinking question. It is going to give you a slope field and ask you whether you think the linear approximation will be an over or underestimate. The trick here is to look at the slope field, imagine at the point given, what would the tangent line look like, and which way are the slope indicators curving compared to your tangent line. And this should help you answer the question. So this is a good thinking question. Quick question, give it a go. All right, last but not least, let's do look at an example of actually working through an Euler's method question. These are calculator questions. They are not convenient by hand for the most part, but otherwise they are not terribly difficult. And it is an algorithm, so it is a routine. It can be a bit confusing, but there is a routine here. All right, so let's take a look at a fairly simple example. We're going to consider the initial value problem, y prime equals xy plus 2y, and our initial condition is y of 0 equals 1, i.e. our initial condition point is at 0, 1. So we are to use Euler's method to obtain a 4-decimal approximation of y of 0.6. So we are trying to evaluate the output of the function that passes through this initial condition point at 0. We are trying to evaluate it at 0.6, at x equals 0.6, and Euler's method will allow us to get an approximation of this. So again, the first thing to note is that this is a first order dE. Slope is given by this expression. So at any particular coordinate point in the plane, plugging your x and y coordinates into this function gives us slope. So that is the idea here, yes? So Euler's method, the formula we came up with says this, yes? So the next y value is obtained from the slope evaluated at the previous point times the step size plus the y value at the previous point. So I think what I find convenient, and I would recommend setting up a tables like this every time you do one of these. This is, I think, very convenient. Again, we can fill a lot of this out fairly mindlessly. The n is simply a counter for which step we're on. We always start at step 0. The beginning is step 0. So we can simply fill out this table, step 0, and then step 1, step 2, step 3, x sub n. So remember that x sub n starts at x equals 0, and if the step size is 0.2, then the x's are going to go from x0 is 0, x1 is 0.2, x2 is 0.4, x3 is 0.6. So notice the setup here is geared to getting us to x equals 0.6. This is the place that we are trying to evaluate our dE at, or our initial value problem at. So I can go ahead and fill out this column, and this entry. That's my initial value. I can do that without having to do any work at all, right? These are our coordinate points of where we're sitting at. This is our first place. We're starting at 0, 1. So the formula says, how do I come up with y1? I do f at x0, y0, slope at x0, y0 times step size plus y0. So I want to do this. This is step size 0.2 times f of x0, y0. So this is f of 0, 1. Put in 0, 1 into that slope function, multiplied by 0.2, I got this to be 0.4. So double check these on your calculator. So that's what we need. Forget about this for a second. This would be what we need to work on. So this is my h times slope value. So in order to get the new y value, I have to add this value here to the old y value. So this plus this gives me this. This plus this gives me this. Add this plus this to get this. Once I have this new value of y, I have my second location at 0.2, 1.4. And then I just repeat this process. I use the coordinate point next at 0.2, 1.4. I plug that into my f function to get my slope value. I multiply it by 0.2. Just for convenience, I put that value in here. I got this to be 0.616. And then I do this plus this added to this, I do this plus this, that would give me my new y value right here. And again, one more step. We do the new point here, plug that into our slope, come up with slope, multiply by 0.2. I got this to be this value. And then this plus this is my newest y value. And at that point, we are done. This is what we were after. At when x equals 0.6, what is our y value? This is the y value coming off the tangent line. That is our approximation for the true value of this, for the true value of the solution to the initial value problem. So again, we are approximating the value of a function that we don't know so far. We haven't decided what that function is. So just forget about this for a minute. Let's just take another look here. And I am not going to talk through the whole thing. It's kind of too boring. These are kind of tedious, lots of tapping on your calculator, but just be clear on the setup. What if we were to do the very same problem and we're trying to estimate the very same value, but let's say instead of stepping over by 0.2, a step size of 0.2 each time, what if we step over by 0.1? So again, we can set this whole thing up. I kind of set up the table to be the right size, but it is something to think about. Again, always start with step 0, and then I need to go through step 6, right? Because we're starting at x0 equals 0, and I'm stepping over 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. That's where I wanted to end up. So I just have to do more steps here using these values. But I kind of start in about the same place. We start at 0, 1. I plug that into that slope calculation, f of xy. I multiply by the step size. This time step size is 0.1, and I get 0.2. And therefore, this plus this equals this, and continue. So we can work our way down. And again, this is very much calculator values. And if you get all the way down, we get to this value right here. And this is our estimate for y of 0.6. Oh, excuse me. This is our estimate for y of 0.6, because that is the y value we got when x is 0.6. So notice I don't need this box right here. There's no harm in calculating it, but it doesn't do anything for us. We are done once we have that value right there. Now you might notice that here are our two solutions. These are both estimates for the same value, and they're not super close to each other. It kind of illustrates that Euler's method is not directly all that great, especially with, again, these would be considered rather large step sizes, so not terribly accurate. So this is more of an exercise by hand than something that is accurate at that level. The rest of this page is just to demonstrate the error. So the rest of the page and these grayed out columns are really just to demonstrate error. So notice, but before we do that, here's a little exercise. There's a little one on my Open Math to try to fill out for Euler's method. So give that a go. And then the rest of this question on this page is just about looking at the error. So it turns out you can actually solve our DE here that we started with can actually be solved explicitly. It is a separable equation, and you can solve it as such. So if you do that, again, you can work it through, check my work, but this is the solution I got for this initial value problem. So this is the function we were actually trying to approximate using Euler's method. So if I come back up, if I use that function I found there, I can use that to fill in these boxes. So this is basically, if this is, excuse me, if this is our function, y equals, or f of x equals, then I can evaluate f of 0 should be this guy. This is f of 0.2, f of 0.4, f of 0.6. Similarly down here, I just evaluated that function, and then I'm really just looking at how does the actual value compare to the estimated value. And of course, at the initial condition, that is a tangent point. So they are in the same place. There is no error. As we make our first step, our Euler's method gave us a 1.4 output, but it should have been 1.522. The absolute error is the absolute value of the difference, or 0.122, and so on and so on and so on. So you can see here, this is what we got by Euler's method with a large step size of 0.2. This is what we should have gotten. So we're a bit off. We're a bit off here. The actual error is almost 1, which is quite large. Probably the interesting thing to look at here is when we reduced our step sizes down, hopefully this should have gotten more accurate because we used a smaller step size. And indeed, you can see, and again, same thing, these are the actual values of the function. These are the errors as computed by doing, again, on each row, I do the difference between this guy and this guy. Absolute value is here. So this one here, 3.37715. That is certainly closer to the true value here than it was. That's the true value. That's certainly a better value, less error than this one. So yes, using a smaller step size and more steps was actually more accurate here. All right, so that's it for today for this video, and we will complete this packet in class together. Thank you.